Today, in this video, we will learn about discrete random variables and probability distribution. This section is the second section of Chapter 6 in Probability and Statistics course. But before diving into the detail, let me require you what is a random variable once again. Random variable is nothing but a function that assigns numerical values to the outcomes of a random experiment. To talk about random variables, we need to understand first what random experiments are. From random experiment, we expect to have a sample space, and over this sample space, we define random variable. This random variable is nothing but a function that assigns numerical values to the outcomes of a random experiment under this sample space. Right? Here, with this notation, for every outcome in the sample space, we map into the real numbers. This mapping is done through this random variable x. Right? So, this random variable by its nature is quantitative. Quantitative random variable. For example, tossing a coin is a random experiment. From this tossing a coin, we will have the sample space. If the tossing is once, the sample space will be h or t. These are nothing but actual outcomes of this tossing a coin once. So, what's the interest with these actual outcomes now? Based on this definition, let x be the number of heads, right? X now is number of heads. Now, this x takes actual outcome, head for example. How many heads in this head outcome is 1. And x into t, how many heads here? 0. The counterpart of this ht in real numbers will be 0 and 1. Based on this definition, x be the number of heads. Now, these actual outcomes generated from the random experiment of tossing a coin now mapped into two numbers respectively, into 0 and 1. So these zeros and ones are numbers or numeric values. What the purpose of mapping the actual outcomes into real numbers is nothing but to describe the random variable under investigation mathematically. For example, for those random variables, we can construct probability distribution. And we can summarize the property of the constructed probability distribution through mean and variance. So, this mapping from actual outcomes generated from a random experiment to real numbers has a great deal in probability, right? That allows us to modeling the numerical properties and the nature of their occurrences. Random variable, as it is quantitative by its nature, be divided into discrete random variable and continuous random variable. What is discrete random variable? Discrete random variable is nothing but a variable takes countable values such as 0, 1, 2, 3. Can be finite or infinite. For example, tossing a coin n times, and if we define x to be the number of heads, so this x is nothing but discrete random variable in this context. Number of children in a family, discrete. Number of car accidents, discrete. Number of defective items, discrete random variable. Number of bacteria per 2 cubic centimeter, discrete, because their values described using these whole numbers 0, 1, 2, 3. In the other way, random variable can also be continuous random variable that takes values from an interval of real numbers, in general uncountably infinite, such as height of students, time taken to finish a race, weight of newborn babies, temperature measured in a city. These all are examples of continuous random variables, right? These all things can be understood from the statistic variable. Variable in statistics is divided into two broadly, into qualitative and quantitative, right? This qualitative variable is nothing but whose value cannot be expressed numerically, such as sex, marital status, region code, religion, and etc. The quantitative variable in general can be expressed by numbers. This quantitative variable can also be divided into discrete and continuous. Analogy to this one, in probability, the random variable can also be divided to discrete random variable and continuous random variable. Right? These all are the two random variables in probability. But here in this video, what the focus is all about discrete random variable and probability distribution. So formally, what discrete random variable in probability is defined below. A random variable x is said to be discrete if the set of its possible values is finite or countably infinite, meaning that x such that x is the functional value of this x into lowercase s, where this s is element of the uppercase s, is finite or countably infinite. Example, tossing a coin twice generates a sample space of h, 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 t, t, h, t, t. If we define x to be the number of heads in each outcome, what will be the possible values of x now? Meaning, what will be the range space for x? It can be either 0, 1, or 2. These are the possible values. The possible values here, which are finite, 0 up to 2. It is finite, and this expression is whole numbers, 0, 1, 2. So these are countable. These possible values are nothing but countable, finite, right? So this random variable is discrete random variable. In short, that we can understand easily. Its associated probability mass function can be defined as follows. For a discrete random variable x, the probability mass function PMF satisfies these two conditions. Every i's value of the random variable, its probability should be non-negative, right? And the sum of all possible values of our random variable should be 1. The probability from A to B is the sum of all probabilities within this range, right? This is the third condition of the probability mass function, right? So for a discrete random variable x, the probability mass function pxi satisfies 1, this one, second this one, third one is this one. Now let us see one example. Suppose we toss a coin 2 times, right? This is the random experiment E, where this tossing a coin 2 times generates a sample space what? H, 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 T, T, H, T, T, right? These are the actual outcomes of this random experiment. So if we define random experiment x here, which is the number of heads in each outcomes, what will be the possible values of this x? This is nothing but range of x. This x can be 0, meaning an outcome with no head, right? 1, an outcome with 1 head. 2, an outcome with 2 heads, right? And we do have actual outcomes that corresponds to these range space elements, right? This 0 means, right, this one, right, x into tt. It's a functional value we have said. And what this one means, x th x ht. We have 2 outcomes whose numeric value is 1. Was this 2 refers x h h 2. In this h h we do have 2 heads, right? So for this random variable, once again we can construct probability mass function or probability distribution. So what's probability distribution? Probability distribution in discrete random variable is a tabular form which consists of possible values of our random variable with their respective probabilities. So probability distribution tells us what are the possible values of our random variable under investigation and how likely each possible outcomes. So here what will be the probability distribution or probability mass function for this random variable? This is nothing but, here with this tabular form we have two rows, x and probability of x, right? This x is lowercase, whereas this x is uppercase, is equal to the lowercase. Through this we do have these possible values 1, 0, 1, 2. So what the probability of x is equal to 0 is, how many actual outcomes do we have whose numerical value is 0, meaning that outcomes with no head. We only one actual outcome, so 1 over 4. Out of this total possible outcomes in our sample space, only one actual outcome yields numerical value 0. So 1 over 4 will be the probability for that possible value. And how many actual outcomes whose possible value is 1? We'll have 2, th and ht. This both yield 1. So 2 over 4 or 1 over 2. We do have one actual outcome with two heads, right? This is hh. So this is nothing but the probability distribution for x, where x is the number of heads, and this tossing a coin twice. So to define this probability distribution, first we need to have random experiment. From random experiment we need to have the sample space. Then over this sample space we need to define what our random experiment represents for. Then we generate the range space of the defined random experiment, upon which we can construct this probability distribution, right? Let x denote the sum of two fair dice. The sample space S consists of 36 pairs ij, where this ij runs from 1 up to 6. So the possible values are this fold: 2, 3, 4, 5 up to 12. Their respective probabilities are given below. What's the random experiment here? Random experiment is rolling two dice, two six-sided dice, right? This is a random experiment. From this random experiment we expect to have the sample space, actual sample space, which is, for example, 1, 1, 1, 2, 1, 3, right? 1, 6 up to 6, 1, 6, 2, right? 6, 6. So these are the actual outcomes from this rolling two dice, right? So given this one, but we are not interested with these actual outcomes, right? Our interest is with the newly defined random experiment, which is x. Here is the sum of the dice, right? We are not interested with the pairs of the dice, but with their sum. What's the range space of x now? Range space of x is all about the sum. For example, 1 plus 1, 2. The minimum, the lowest sum is 2, because this starts from 1, 1, these pairs, and 1, 2 is 3, right? 1, 4, 1, 3 is 4, and up to 12, right? The maximum is the sum of 6 plus 6, right? So from now onwards we will talk about this range space, right? That mapping these two with the actual outcome. How many mapping outcomes are there for the range space element of 3? This is nothing but 2, right? 1 and 2. Let me turn back here, right? It is not complete this one. So here, based on this defined random experiment, we can construct probability distribution. The possible value 2 has an actual outcome 1 1, right? This is the only actual outcome that yields sum 2, right? And these two actual outcomes with sum 3 each. 1 plus 2, 3, 2 plus 1, 3. And how many actual outcomes whose sum is 4 each? We do have 3. The probability is also 3 over 36, because from tossing 2 fair dice, 36 pairs are expected. So the total outcomes in our sample space 36, and these favorable outcomes are based on their possible values of our random experiment, right? For example, the probability of x equals to 5, 4 over 36. So how many favorable outcomes are there whose sum is 5 each, right? We do have 1, 2, 3, 4. 4 over 36. The same is true. Here is highest favorable outcomes. How many favorable outcomes whose sum is 7? These are 6. 1, 2, 3, 4, 5, 6. So the probability goes to 6 over 36. Therefore, this element with this element, right, is a probability distribution. We can see from this one. The probability mass function or probability distribution for the random variable x, where x represents the sum of the dice, is nothing but given by this table. So from this probability distribution, we can understand that what values the random variable can take, this row, and how likely each value is the second row. And from this probability distribution, we can easily compute the expected value of the random experiment and the variance of these possible values, right? And graphically, this probability distribution can be presented using this bar chart. This bar chart is symmetric by its nature, where the maximum probabilities has sum 7, and the minimum as the lowest possible value, and the maximum possible value of the random experiment, right? So this is nothing but symmetric, right? Was the signal which is conveyed through this probability distribution and through this probability distribution is the same. The same is true. Tossing 3 coins at a time generates this sample space, right? If x is defined to be the number of heads, what will be the probability distribution of this x is the question. The probability distribution is nothing but given by this one, where the possible values are 0, 1, 2, 3. This x is discrete random variable because the possible values expressed in whole numbers or countably whole numbers, and their respective likelihoods expressed by this row. The probability of getting an outcome with no head is 1 over 8, right? We do have 8 outcomes, from which there is one favorable outcome with no head, right? The probability of x is equal to 0 is nothing but 1 over 8. This is 1 over the whole 1, 2, 3, 4, 8. So probability of x is equal to 1. How many outcomes with one head? This is one head. How many outcomes are there with only one head? One is this, one is around, another is here, 3. Therefore 3 over the total n into s is 8, 3 over 8. The same is true. The probability of getting outcomes with two heads will have 3. The same is true. Right? So this is nothing but the probability distribution for the random variable x, which represents the number of heads in tossing a coin 3 times. The counterpart of graph presentation is given here, right? Where the highest probability tends to with the possible values of the random experiment 1 and 2, whereas the least with 0 head and with actual outcomes with 3 heads, right? Learning activities. A family will have 3 successive children with sample space of this, right? Boy, 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 girl, girl, right? We don't know. In the next, a mother may get birth, boy or girl, but we do have this sample space, right? In successive births, may get birth 3 boy or 2 boy, 1 girl, or 3 girls. So the possible outcomes of the mother's successive births will be this sample space, right? Now, over this sample space, we can define a random experiment x, which takes values number of girls, right? Now, for this random experiment, you are asked to solve this. Determine the possible values of x. Construct the probability mass function of x. Calculate the probability of x greater than or equals to 2. Calculate the probability of x less than or equals to 2. What does it mean, probability of x less than or equals to 2? Meaning that the probability of getting outcomes with girls 2 or below, right? With 2 girls or below. These are nothing but we count the outcomes with 2 girls, right? 1, 2, 3, 4, and below 1, 2,